All right, let's dive into one of the biggest ideas in all of statistics. How can a tiny little piece of information tell us something reliable about, well, the entire world? It's all about making these huge conclusions from small bits of data. And we're going to break down exactly how it's done.
I mean, it seems kind of like magic, doesn't it? You poll just 1,000 people, a tiny fraction of the population, and somehow you can predict how millions are going to vote. Well, that's the power of inferential statistics, and it's the core question we're going to answer today. How do we make that incredible leap from a small sample to the big picture?
So, here's the fundamental challenge every statistician faces. We can almost never survey everyone or measure everything. It's just not practical. We have to work with a small piece, a sample. And the real dilemma is figuring out how to use that one sample to say something meaningful and, more importantly, reliable about the entire population it came from. Okay, this slide right here, this holds the key to the whole thing. Just imagine for a second. Imagine you could take every single possible sample of, say, 100 people from a country. You calculate the average height for each sample, and then you plot all those millions of averages on a graph. That graph, that beautiful bell curve you'd get, is the sampling distribution. Now, in the real world, we only get to see one of those samples. But knowing this theoretical distribution exists is what lets us confidently guess where our one little sample fits into the grand scheme of things. So with that theory in our back pocket, we can build a really practical tool. We can finally move from just making a wild guess to creating a range of possibilities that we have a specific level of confidence in. Think of it like trying to catch a fish. You wouldn't use a single spear, right? No way. You'd lose a net. Look, we have to be real here. Our single sample probably isn't a perfect, exact match for the true population average. So instead of making one single pinpoint guess, which is probably going to be wrong, we build a range. That's our statistical net. We can then say something powerful like, we are 95% confident that the true population average is caught somewhere inside this net. And that, my friends, is a confidence interval. And the way we build this net is actually pretty straightforward. You take your sample's average, and that's the center point. Then you just add and subtract a little margin of error to create the full range. That margin of error is made of two key parts: a multiplier that depends on how confident you want to be, and something called the standard error, which basically measures the typical wobble or variation between samples. And here it is, probably the most famous multiplier in all of statistics, 1.96. If you want to build a 95% confidence interval, which is really the gold standard in a ton of fields, this is your magic number. You are going to see this number everywhere. Of course, 95% isn't your only choice. If you only need to be 90% confident, you can use a smaller multiplier, 1.65, which gives you a tighter, more precise range. But if you need to be super sure, like 99% confident, you're going to need a bigger multiplier, 2.58, which casts a much wider net. See the trade-off? It's a constant balancing act between how precise you want to be and how confident you need to be. Okay, so confidence intervals are awesome for estimating a value. But what if you want to test a specific claim? Let's say a company claims their new light bulbs last for exactly 10,000 hours. To test a claim like that head-on, we need a different kind of tool. We need a hypothesis test. And one of the most common ones is the z-test. Now hold on, you can't just bust out this powerful tool whenever you feel like it. There are a couple of key rules. First, your sample size needs to be pretty big. The usual rule of thumb is 30 or more. And second, and this is a big one, you have to already know the standard deviation of the entire population. That's kind of rare in the real world, but it definitely happens. Before we even look at the real math, which can look a little scary, the idea behind it is incredibly simple. A z-test just asks, how different is the thing I actually observed in my sample from the thing I expected to see? And it measures that difference in units of standard error. Basically, is the difference we found a really big deal, or is it just the kind of random noise we'd expect? That's all it's asking. So here's how that simple logic translates into the actual formula. Up top, you've got the sample mean, which we call x bar, minus the hypothesized mean, or mu. That's just what we saw minus what was claimed. Then we divide all that by the standard error, which we calculate using the known population standard deviation, sigma, and our sample size, n. As you can see, every one of these symbols has a very specific job to do. This whole process might seem a little complicated, but here's the good news. Statisticians have developed a rock-solid, 4-step blueprint that you can follow every single time to get a clear, reliable answer. So let's walk through that blueprint right now. Here it is, the master plan. Step 1, you state your two competing claims, the null and the alternative hypotheses. Step 2, you find your critical values. This is basically drawing your line in the sand. Step 3, you actually compute the test value using your sample data and that formula. And finally, step 4, you make a decision by comparing what you got to that line you drew in the sand. Simple as that. Okay, theory is great, but let's make this stuff real. We're going to walk through an actual example from our source material, step by step, using that 4-part blueprint. This is where the rubber meets the road and it all starts to click. So here's our scenario. We went out and measured 400 men, and we found their average height is 67.47 inches. Now, we happen to know from historical data that the population mean is supposed to be 67.39 inches, with a standard deviation of 1.3 inches. So the big question is our sample of men significantly different, or is this tiny difference just random chance? Step 1, we state our hypotheses. Think of the null hypothesis, H0, as the default position, the status quo. It says, nothing special is going on here, our sample probably comes from that known population. The alternative hypothesis is the challenger. It says, nope, something's different. The mean isn't what you think it is. Our job is to see if we have enough evidence to support the challenger. All right, step 2, we set our boundaries. We're going to use the standard 5% significance level, which corresponds to our old friend, the critical value of 1.96. So we have boundaries at positive and negative 1.96. If our final calculated number falls outside this range, in what we call the rejection region, we'll decide our result is significant. And now for step 3, it's time to crunch the numbers. We just plug everything we know right into the formula. So that's our sample mean, 67.47, minus the hypothesized mean, 67.39, and we divide all of that by the standard deviation, 1.30, over the square root of our big sample size, 400. And when we run that calculation, the results, our z-score, comes out to 1.231. This is it. This is the crucial number that tells us exactly where our sample result falls on that theoretical distribution we talked about earlier. And now, the moment of truth. Step 4 is the decision. We take our calculated value, 1.231, and we compare it to our critical boundary of plus or minus 1.96. The question is simple. Is our value more extreme than the boundary? And the answer is no, not even close. Our value of 1.231 falls safely inside the boundaries of negative 1.96 and plus 1.96. So what does this mean? It means that while our sample's average height was a little bit different from the population mean, it wasn't different enough to be statistically significant. We simply don't have the evidence to reject that default nothing special is going on hypothesis. So what's our final official conclusion? Well, based on our z-test, it's totally reasonable to believe that this sample of 400 men is just a standard random sample from the population we were testing against. The small difference we saw? It can easily be explained by nothing more than random chance. So there you have it. We went from a small sample all the way to a confident statistical conclusion. This 4-step blueprint is an incredibly powerful way to test claims and find real answers in data. The only question left is, now that you have the blueprint, what questions about the world are you going to answer?